Hello, my name is Joao Penedo. I'm a postdoc at INFN Roma 3, and today I'm going to tell you about a work done in collaboration with Alessandro Granelli, Davide Meloni, Matteo Paricciata, and Sergei Petkov. And the idea is to join modular flavor symmetries and a low-scale symmetry-protected seesaw. We start from our motivation, which is essentially the flavor puzzle. So we see in nature some hierarchies between fermion masses, some patterns of fermion mixing, and we'd like to explain them as well as the observed magnitudes or yet unobserved magnitudes of CP violation. In particular, if you look at this part of the hierarchies, we have a very light neutrinos, and we would like to explain also that. We are starting to constrain experimentally from tritium or cosmology the allowed region for what the values that these masses can take, but they are quite small. And so theoretically, we think, let's say in the SMEFT, that they can be the first deviation from the standard model, suppressed by a large scale, leading to this Weinberg operator. The easiest UV completion you can think about is the type 1 seesaw, where you add gauge singlets to your theory. Then neutrino masses will be essentially proportional to these Yukawa matrices in flavor space and this inverse Majorana matrix. Now, the seesaw here actually has a feature. These are matrices. They are not numbers. So if you think of them naively as numbers, you see that there is a trade-off between, oh, I need a high scale if these couplings are order 1 to get light neutrino masses. Or instead, if I have low masses, I just need to have small couplings. And this is the naive, let's say, unprotected scenario. However, to have something which is collider testable, you need an accessible mass, so you need a low scale and at the same time large enough couplings to produce the new states. Such a thing is actually possible because these, as I said, are matrices. So you can engineer some cancellations, and as long as they are protected by some symmetry L, you can really have a testable scenario, which gives you light neutrino masses. So how does symmetry protection of a seesaw work? It's essentially based on approximate lepton number symmetry L. So it's called non-standard because the new right-handed neutrinos have these non-standard charges. But if you have an approximately conserved such symmetry, you could have, let's say, the Majorana mass matrix be at the, let's say, GeV scale and keep the light neutrinos light. Now, if L is exactly conserved, what you get is degenerate massless light neutrinos, while the heavy neutral leptons form a Dirac pair. As soon as you break slightly this symmetry, some epsilon different from 0, you can split the Dirac neutrinos into a pseudo-Dirac pair and produce delta m square atmospheric and delta m square solar. So in the limit of exact L symmetry, we would have something like this, no neutrino masses, and a pattern which is like this. You can check that through matrix multiplication, things cancel out and you get no neutrino masses, except for the heavy guys, which form a Dirac pair. As soon as you turn on some small lepton number breaking, if you do it, for instance, in YD, you will get some splitting, which is small of the same order of neutrino masses. But you see that you share the burden between the usual y square over m and this epsilon. So you don't need to, you can have large Yukawas and not so big m because some of the burden is taken by epsilon. If you also turn on something here, this will be qualitatively the same, but you can attain larger splittings of the heavy neutral lepton pseudo-Dirac pair. Okay, now let's discuss the modular symmetry approach. We need this as a flavor symmetry. It's something that will unify generations. It's orthogonal to the GATT. And we are trying to go beyond the traditional approach, which is based on abelian discrete flavor symmetries. This is an approach which works well for some things, but has some problems. And the problems usually involve building a potential for the fields that break the symmetry group. So you really end up having to do a lot of model building with shaping symmetries to tame the flavon potential. The idea of modular symmetries is to revert the logic, and what you do is instead of postulating the symmetry group and then see how you need to break it in some aligned direction, you think, no, what is the simplest symmetry breaking setter I can have? And from that, go in the direction of the group. So this is the approach of modular symmetries introduced by Ferulho in 2017. It has a cape also because it's inherently supersymmetric, and it does away with these flavon fields. So essentially, in the minimal idea, you can just depend on a complex scalar field tau, which is called the modulus, and you would be able to use it to obtain, one hopes, the observed patterns of fermion masses and mixing. Now, this modulus, while from the top down it can describe a compactification, from the bottom up we just take it as a spurion. Nevertheless, the idea behind the modular symmetry is that different taus describe different compactifications, different physics, unless they are related by this fractional linear transformation with a, b, c, d integers and determinant 1. So the set of all these transformations makes up the modular group. And it's this redundancy in the description. The field tau is then the field that breaks your symmetry. Let me just skip some details on the group, but we can discuss them if you'd like. The point is that as soon as tau gets a vev, the symmetry is broken. We are maybe more interested in how the usual fields transform, and the fact is that they transform like in the previous usual approach of flavor symmetries, but with an extra factor, this so-called automorphic factor, which depends on a charge or so-called modular weight kappa associated to the field. Even though the modular group is infinite, the trick here is that you make the fields blind to a so-called principal congruence subgroup of it. So it's like you quotient an infinite group by an infinite subgroup, and you get a finite group, which are the modular finite groups. And the nice thing is that these groups are isomorphic to the usual A4, S4, A5 that is used in traditional flavor model building. So this raw matrix here will be a representation of this finite group. And the automorphic factor is essentially the novelty. These groups have been studied, each in these papers. I will not go through the details. There is a lot of literature. I just want to tell you that as soon as you start building your invariant theory, you need not only the fields, but somehow to introduce tau there, because all the transformations of the fields, these factors and these rows, need to be cancelled by an appropriate transformation of this function y of tau, which transforms in a way that cancels these exponents and these rows into a singlet. The nice thing here is that the functions which behave like this under the modular transformations are known to mathematicians. They are so-called modular forms, and for each weight kappa y, there is a restricted number of these functions. Therefore, we see here how the setup could be predictive, because for each weight and each group, you only have a small set of y's to use to build your Yukawa matrices and your mass matrices. So for instance, if you look at modular A4, you only have at weight 2 a triplet, and that's it. That's the only thing you can use to build terms. I will skip a bit of details, but give you directly an example. So if we want to build a Majorana mass term in our superpotential in A4, and this right-handed neutrino transforms as a triplet of weight 1, the term will need an insertion of this function of tau. This is the only one you can do, and the only thing you can have is this Majorana mass matrix. Note that it depends only on tau via these special functions, which are well known. If you peek under the hood, they have nice expansions and relations. But aside from tau, they will only, in this example, depend on an overall factor. So it's quite a constraining setup. And we can build models. Let's go to something more realistic. Here we have an S4 lepton model, which we discuss in this paper. You choose your field content, your group S4 modular version, and you can build your superpotential. Again, each of these terms will be a singlet, so each under the hood will be some kind of special matrix structure that depends mostly on tau and then on some superpotential parameters, alpha, beta, g's, and so on. Then you can try to fit your couplings to data and see if you do get a good fit to neutrino data. One thing you can do to reduce the number of parameters is to impose a CP symmetry, more on that later, which will make this G prime real and reduce your parameter count by 1. So if you do so, really, we are in the second paper here, we find that you can still fit the model to data. You get some interesting correlations and some predictions for the octant of θ23, CP violation phases, and beta beta, and so on. Now, another comment here is that when you do this fitting, you don't need to consider the whole complex plane where, or upper complex plane where tau lives. Interestingly, since you can map any value of the modulus VEV into this blue region, the fundamental domain, you only need to scan the fundamental domain to try to fit your model, since points outside are indistinguishable from points inside. Now, let me briefly comment on the fact that CP and modular symmetry can also be consistently combined. In this case, what CP invariance does is that it makes your superpotential parameters real in the appropriate basis, and the tau under CP goes to minus tau star. This means that unless you are in tau and minus tau star are related by a modular transformation, so unless you are in one of these special green lines, your CP will be broken by the VEV of tau. If you are on one of these lines, the VEV of tau will conserve CP, and so your theory will be CP invariant. Are there other important points in this fundamental domain? The answer is yes. There are these 3 points: the corner of the fundamental domain omega, the point I, and I infinity, because even though any value of tau breaks the modular symmetry, it's a spurion. If it stays at one of these special values, it preserves a residual symmetry, Zn, Z2, or Z3, depending. And the key idea of this paper down here was that this could be used neatly to explain mass hierarchies of fermion, of the fermions. Because if tau sits at a symmetric point, your mass matrix may look like this, with many zeros. If you deviate with some epsilon from the symmetric point, you lift the zeros by some powers of epsilon determined actually by group theory. So to give you an example, let's say you are working modular A5 finite group and you have some triplets which decompose in this way. If tau is not I infinity but has a large imaginary part, you can expect to find a mass matrix like this, which is nice because it can lead to a hierarchical fermion spectrum. And this is the mechanism we really want to be at play also when we build the models we will see next. Hierarchies give us a small parameter epsilon. Can we also use the same epsilon to produce a modular symmetry-protected seesaw? And the answer is yes. So our goal is to use the same epsilon, the deviation of tau of the modulus VEV from a symmetric, one of the 3 symmetric points, special points, use it as also the parameter that represents the approximate breaking of the non-standard lepton number. So when you set epsilon to 0, you should recover the conservation of lepton number. And when you slightly break it, you not only produce, let's say, charged-lepton hierarchies, but also you break L and you produce neutrino masses and a splitting of the Dirac particle. So what are the steps to finding these models? The first one is quite technical. I mean, triplets are necessary to reliably interpret epsilon-based hierarchies. This is we can discuss this step if you require. But essentially, you start asking for conditions like this matrix here, the MR Majorana matrix should have this kind of Pauli-like structure when epsilon goes to 0. And this is a cut, let's say it's a filter. The next filter is to ensure the Dirac structure in this Yukawa matrix YD when epsilon is 0. So either this or this, depending on having 2 or 3 right-handed neutrinos. And you need, of course, to verify that your charged leptons can be hierarchical. So the matrices you can obtain are things like this, for instance. Now we did a survey of the landscape of possible models that pass all these filters, and it would be too much to show you these tables. You can find them in appendix, but I can summarize some conclusions. So first of all, not all of the models that we find and list in these tables in the appendix are actually models that can accommodate the data. We will look shortly into 4 benchmarks which do, but not all models you invent in this way will be viable models. The groups that you are driven to, if you choose low weights and small groups, are essentially the double covers of A4 and S4. And the interesting symmetric points are this omega, this corner of the fundamental domain, if you recall, and tau equals infinity, the large imaginary part. Depending on representations, you will have different qualitative predictions for the splitting of the pseudo-Dirac pair of heavy neutral leptons, which can be ranging from the very small to the largest epsilon times the Mariner scale. Finally, let's look at some benchmark models. Here are 4 benchmark models we chose that do fit lepton masses in mixing data. We scan them using multinest. And as an example, let's focus here on model B, which is based on modular A4, and tau lives close to the corner omega of the fundamental domain. Here are the expressions of the mass matrices and Yukawa matrices. It's not very illuminating, but you already see that beside depending on tau, they depend on some superpotential parameters, alpha, g's, lambda. In total, this model has 8 dimensionless parameters. We have imposed GCP. Now, if we rotate to the appropriate bases, maybe this structure with the epsilons becomes apparent, which is nice. And you see that this model really, as a check, does what we want. So the electron muon and tau mass are hierarchical, or they're, let's say, functions of order 1 things times some power of epsilon. And also the big Majorana full neutrino mass matrix has the structure, symmetry-protected structure in the limit epsilon goes to 0. So the viable regions for tau that we find are in line with what we expect for each of these models. A and B are here, this is a zoom, they are close to omega, while C and D are, let's say, viable in regions where tau has a large imaginary part. Moreover, these you can find in some, but not many, correlations between parameters. Here is in benchmark C between θ12 and θ23, and in benchmark D between θ12 and the sum of neutrino masses, things that will be tested in the future to high precision. Other predictions, I will just flash them here. I mean, for A, B, and D, we have normal ordering, but still M beta beta is above the milli-electron volts threshold. We have, unfortunately, CP conservation in the sense that we are too close to a symmetric point to expect something different. And we have also predictions for the splitting of the heavy neutral leptons. Heavy neutral leptons will also have their own phenomenology. These are the usual triangle plots in flavor space. And the nice thing is that they occupy very specific, small and distinct regions of the flavor triangles, which means that one could in principle distinguish between these models. Here we also show how these models could be tested. So this is the exclusion, prospective exclusion in the mass coupling squared plane for the different models. And we see that one distinguishing feature is that they will be probed to some extent, and they are always above the seesaw limit, thanks to epsilon. So in summary, I hope to have been able to tell you that modular symmetries can really offer a predictive framework which would provide an origin for CP violation, explain fermion mass hierarchies, and via a common epsilon, the deviation from the symmetric point, help explain the smallness of neutrino masses, and perhaps produce intensity frontier testable signatures of heavy neutral leptons. In the future, perhaps in a unified way also for quarks to give CP violation. Thank you for your time.